So in this topic, we look at managing comparisons. And to look at this, we use the permillet growth in the Sahel example, which, as always, back in topic 1, we have a little bit more information on this, including the paper that's related to it. And we dig into bits of the paper in here to help illustrate managing comparisons. But first, as a little overview of this case study, the pearl millet growth case study aimed to understand what factors affected how pearl millet grew in different places. This was a 3-year experiment with millet, and it compared 4 different data types to assess their effectiveness in reducing variation. So we're going to first look at the study layout. Now, the physical layout of the treatment affects the comparison of treatments. Before performing the experiment, the researchers check the field to ensure that one area of the field does not impact one treatment more than another area. For example, you might have that part of the field has trees around it, or is by a building, and so therefore has shade on it, getting less sunlight. If you put all of one treatment over there, you might find that that treatment looks to not perform as well, but it's not because of the treatment, it's because of these external factors, the shade. You might have one area, if it's on a slope, you might have kind of one area of the field is closer to a river or by a river, and that area might perform differently to another area. So you don't want to have kind of all of treatment B here and all of treatment A up there. Because you might see that you might say, okay, well, one treatment performs differently to another, but actually that's not because of treatment differences, that's to do with where they've been laid out. That's what we mean by the physical layout of the treatment affects this comparison. Before performing the experiment, as we said, the researchers check the field to ensure that one area of the field doesn't impact one treatment more than the other area. And they found that overall the field's mostly even. There's no noticeable slopes, except for a few spots which looked a little bit different. Initially, the cause of these spots were not identified. And hence, they decided that the treatments could be completely randomized in the field. So here we have an image, which is the layout of the study, is the field, and looks at the history of the land use. And this comes from the paper, which is given back in topic 1. Now, a farmer who used the site before it was fallowed in 1983 helped to identify the previous position of where trees, bushes, termite mounds, hard soil, and fertile areas were. Based on this, because this might affect how the treatments behave, this might affect the outcome, because these are all things that might, they change the soil, and therefore they can change the yield, and so it might make one treatment look to perform differently to another when it shouldn't. But they categorized the plots into the 5 categories based on these informations. And that's kind of what we see in this here. We have these little numbers of 1, 2, etc. So of our different areas. So 1 is the plots that formerly had hard pans, which is associated with poor millet growth. So that's obviously treatments placed there. We're going to maybe expect them to have a poorer growth, and that will be to do with previous use of this bit of land rather than the treatment itself. We also have in 2 plots with former bushes and trees. In 3, we have the termite mounds. In 4, we have the areas of former trash disposal, which is associated with good millet growth, which means that our treatments placed in area 4 might actually look to perform a little bit better. And that will be based on previous use of the land rather than the treatments themselves. And so that's really important to know at this stage, so we don't attribute those changes and that good performance to the treatment necessarily when it might not be to do with the treatment. And then in 5, we have all other plots. So you can see kind of, termite mound, and there was a termite mound there and here, and oh no, that's hard pan, sorry. Hard pan of these ones. Termite mound is 3, so there's our termite mound, things like that. And so if we instead want to color code it to look at it this way, we can, maybe this is easier for you, it's easier for me anyway, just to kind of get this idea of how everything was laid out beforehand, of how the field was used. Then yeah, in yellow we have our plot 1 of the hard pans and so forth, with blue being all other plots. So when, and I know we're talking about the design, but this is where it gets a bit interesting in this case study. So when they were analyzing the data, in the analysis, the researchers noticed a pattern in the data indicating that the west was different to the east on the field. So our north is based kind of in this direction towards the top left-hand corner. That was me checking where left is, if you call that. I don't know if the camera called that, but I was literally just checking that this is the left. But yes, so the researchers noticed, so if our north is around here, then our east is kind of this bit of the field. Towards the top of the field is our east, and towards the bottom of the field is our west. When analyzing, the researchers noticed a pattern in the data indicating that the west side of the field gave different results to the east side of the field. They hypothesized that this is due to a major pest called the cotton stainer, which is common to the west of the field. But to understand it better, they divided the field into 8 sections with 12 plots each. They included how far each plot was from the west side in their analysis. The pattern from east to west was most obvious for grain yields than other yields. So here are our 12 plots, and here are our 8 sections. And this is to look at how far each plot was from the west side in their analysis. So the west is down here, pretty much at the bottom of our plot. And so if we kind of look at our kind of 8x12 table here, instead here what's being put on here is information on the differences, the residuals, which is kind of, as we say down here, these are the differences between the individual plot yields and the respective treatment averages. We don't need to worry too much about what that is, but just as a general thing, this is about how our different, how the results differed as we went from west to east. So as we said, the bottom of the plot is the west, and we see that our numbers are lower towards the bottom of the plot. We have kind of negative 0.36 is our average difference on the bottom of the plot, and plots with negative residuals have lower yields than predicted by the model. So towards the bottom, we have lower yields because we have more negative values, and towards the top of the plot, we have higher yields because we have these more positive values. And we see that in the Stover dry matter and in the grain yield, so in 2 different things. So here's quite nice. You can see at the bottom in the west side, our we generally had a lower yield predicted by the model. Again, in our bottom half, where they're all negative in our bottom half. So well, on average, our bottom half had a lower yield predicted by the model, and on average, our top half had a higher yield predicted by the model, with the highest than predicted being the top, being the most east side, and the lowest being the most west side. So here I've just got up a little bit bigger about grain yield for us, in case that last one was a bit too small. But just having a little look at how our 8x12 plots alter across. What could be interesting as well is to look at that with our sections taken into account too. I didn't actually plan to say this, but you know, we saw here, so I'm not sure what we will find here, but remember we saw areas of former trash disposal to be associated with good growth, and with hard pans to be associated with bad growth. Well, let's just remember that this top right one is associated with bad growth, and these ones here are associated with good growth. And see if that's still the case on average here, just out of interest. potentially is. I mean, 0.03 here compared to these much larger values here, but you know, all four of these values in that corner are no. Anyway, that was just a little side thing that I just thought might be quite fun to look into. I'll let you dig into that, and maybe I will too in my own time. So what's happened here is we've taken that grain yield and we've now colored it in based on those values, just to help us see as a heat map how our positive and negative values change. So the more green values are for our higher values. So here we had 0.91, and that gives us our greenest value. And remember, higher values are associated with better yield. So we can kind of see, okay, around here we've got higher yield. We can see kind of higher yield in general towards the east and lower yield in general towards the west. And here's our lowest yield, or should be our lowest yield because it's the most red, at negative 0.91. So the pattern from east to west was the most obvious for grain yield than other yields. And as said in the paper, the post-stratification of the experiment in the west to east direction contributed significantly to the explanation of total variation. This was indicated by the decrease of residual mean squares for grain yield by 23%. So when we look back at this, we're just talking about this change in the grain yield. We've got grain yield here. We're looking at how this grain yield changes as we go from east to west. Well, how it decreases from east to west. And they say it's by 23%, but they're saying that this is what contributed to kind of explaining those differences in the outcome. And so hopefully this helps illustrate how the layout of your experiments can affect the results. And here the layout of the experiment actually found that those treatments put towards one end of the field resulted in lower yields than at the other end of the field. And this helped explain a lot of that variation in their differences. So overall, the physical layout of the treatments affects the comparison of those treatments. In this paper, they found that the west side of the field has a major pest, or that's what they hypothesized. If they put one treatment in the west and another treatment in the east, it would be unclear if that was a treatment effect or if it was due to pests. Fortunately, because they did random throughout, that's how they were able to then that helped them identify, saying, okay, well, we randomly put our treatments throughout here, but actually our east is performing a lot better than our west. But our treatments are randomly scattered throughout. Why might this be? And that's where they hypothesized about the pest. Hopefully that was a little bit, hopefully that was helpful in just introducing this kind of idea of how the layout of the treatments affects the comparison of them. Thank you.